In today's lecture, we are going to start second order ODEs, second order ordinary differential equations. Now, in lectures, we've already discussed first order differential equations and had a look at some of the solution methods. In particular, the subject of this lesson is these second order ODEs that are so-called homogeneous and they have constant coefficients. Okay. Now, I have already hinted at this a little bit in previous lectures, but the motivation for studying differential equations can be traced back to modelling. Okay, so we live in a dynamical world, and differential equations are used, sometimes in a very crude way, to model these dynamical processes, dynamical phenomena. If we set up a differential equation and then solve it, hopefully what the solution gives us is more information about future states of our model or past states. So we can actually predict the behavior of the future behavior of the phenomena that we're looking at. Okay, so here is an example of a general second order differential equation. Okay, the unknown function here is y, and p, q, r, and g are all given functions of x. In particular, sometimes we couple this general differential equation with some extra information called initial conditions. Okay, so we know the value of the solution at one point and the value of the derivative of the solution at that same point. So this kind of problem, that underlying problem, is known as an initial value problem for second order ODEs. So, you know, as a basic example here and kind of along the lines of the problems that we'll look at, think of this problem here. Something like that. Okay? The problem on the right is a much simpler version of the general setup there, because the coefficient functions, the p, q, and r, are all constant functions. Okay? And in fact, some of you may remember these kinds of equations. Okay? Now, the theorem that is kind of surrounding the equations under consideration is very powerful. Okay? Suppose that these coefficient functions, these p, q, and r's and g's, are all continuous functions, and that p is never zero, has no zeros. Then the initial value problem, a general initial value problem, has one and only one solution. Okay? So what's the significance of this result? Well, it gives us a hunting license. If we're given some sort of ODE with some initial conditions, like the one on the right, that theorem says if I go and try to find a solution, well, one exists, so I'm not looking for something that doesn't exist. You know, looking for a black cat in a dark room that's not even there, right? The point is that this theorem gives us a hunting license to go out and hunt for the solution. We know it's there, we just got to construct it somehow. Okay, so this is overlooked many times when you first see ordinary differential equations. You just assume they're solvable. Well, they're not necessarily anyway. Okay, so the subject of this presentation is all about the following problem. Here A, B and C are just constants. So, something like this might be a special case of this problem up here, or something like this. And in particular, the coefficients of the derivatives in the function in the ODE are all constants, okay? They're constants. Now, we call this particular general form, the DE one, homogeneous or homogeneous, due to that 0 on the right-hand side. Okay, so whenever you see 0 on the right-hand side here, you would, that's what we mean when we talk about homogeneous second-order problems with constant coefficients. Now, what we like to do, like any equation, is solve these kinds of problems for the unknown function y. Okay, so the thing we're looking for is a function, not a number, a function that satisfies the given differential equation. Okay, now you might think, well, what's so interesting about this particular problem? Well, it's a basic first approximation to lots of physical processes. Vibrations is a good, a basic model that we can use this to describe the dynamics of what's going on. And indeed, we'll look at vibrating systems at the end of this section where we apply all the ODEs. So, how do we solve this general equation, differential equation, and what is the form of the solution? Now, some of you may already know what the general form of the solution should be, but I wanted to actually speak a little bit more about that. So if you've studied, say, a second course in calculus, you would know that, well, to solve this particular problem, you write down a special polynomial equation called the characteristic equation, and you look at the roots, and then you write down the solution. Well, I'm actually going to do this one a slightly different way, to actually show you where the solution comes from. Okay, so the methods that we learn in first year generally give us no indication about where the method, where the type of solution comes from. We can solve it, but it doesn't tell us anything about how you construct the solution. So what I'm going to do is solve this by reducing it down to a first order problem. In particular, I'll reduce it down to a first order linear problem that we know how to solve. Okay? What I'm going to do is split up this minus y prime. So you might want to draw a little line down here and sort of form two columns. So I'm going to rewrite 2 as the following. I'm just going to split up this minus y prime term in the following way. Now, it's not clear why I've actually done it in this particular way, but it'll become clear at the end. Okay, so I've split that y prime term into two parts. And what I can do is sort of team these guys up and team these guys up and form the following. I can take out a common factor of 2 from these two terms. Now, if you look at what's in those brackets, you can see, hopefully, that that is just the derivative of that bracket. Okay? Can you see that? So if I differentiate what's in here, I get that. So what I can actually do is take like a d dx out the front of that bracket, and we have the following. Now, what I'm trying to do here is reduce that second order problem down to something that we already know how to solve, like a first order problem. And if you look carefully, in the square brackets, we've got the same thing. I've got the derivative of something here plus 2 times that same thing equals 0. So what I can do is make a substitution, say u equals what's in those square brackets, and form a basic first order problem. Minus 3y. So y prime minus 3y. So what will this become then? This will just become du dx plus 2u equals 0. Or just u dash plus 2u equals 0. So how do I solve u dash plus 2u equals 0? Well, it's an exponential function, something like e to the minus 2x. Let's call, use a constant k, let's say. Okay, so k is an arbitrary constant here. So I've solved that problem. What I can do now is back substitute into this problem. Okay? So if I sub that back in there, it's a first order linear problem, and I can find the integrating factor and solve. Okay? So back sub u into star to form, what are we going to get? We're going to get y prime minus 3y equals k e to the minus 2x. Now this is a first order linear problem. Okay, so remember, to solve first order linear problems, I look at the integrating factor. I form the integrating factor from the coefficient function here. In this case, it's going to be minus 3. Okay, so for this problem, the integrating factor, let's write it as v, say, is just e to the integral of minus 3. So it's just e to the minus 3x. So if I multiply both sides by this integrating factor, the left-hand side is just collapses to the following derivative of this product. And the right-hand side will be that times that, which is k e to the minus 5x. Now, to integrate, to find y, all I do is I integrate and then rearrange. So I integrate this, I'll get something like k on minus 5. Let me start that again. So if I integrate here, I'm going to get something like plus some constant, let's say b, integration constant, and then let's just bring this to the other side. So I have y. So when I bring this to the other side, I'll get something like this. Now let's just make this constant a bit nicer, and I'll just write it in terms of a and b. Okay? Now of course that's a long way of doing it. You wouldn't do that if you were presented with that problem, because it's rather long, right? But it does tell you why there is two exponential functions in the answer. Okay? So the k is just an arbitrary constant, right? So it just comes from the integrating factor up here, from the constant of integration. All right? Now, you wouldn't solve that if you were given this problem in an exam or something, right? All I'm trying to do is to show you that this particular problem has a special form of the solution. It involves exponential functions, and maybe you can see I've got a minus 2 and a positive 3 here, and I split up this middle term into something like, well, just with the signs changed, minus 3 and positive 2. And furthermore, if I multiply these two numbers together, the minus 2 and the positive 3, I get that coefficient, minus 6. Okay, so we have a linear combination of special exponentials, this one and this one, right? Now, you can actually verify that each of these functions are solutions to this problem just by differentiating each of them twice and putting them in here. Okay, well, how did I know to split up the thing into minus 3 and positive 2? Well, you can see the coefficient minus 1 is basically split up into minus 3 plus minus 2. Now, positive 3 and negative 2 occurs in our solutions. And like I said before, if you multiply 3 and minus 2, you get the coefficient of y, minus 6. Now, essentially when we solve these problems, we solve a resulting quadratic equation, a characteristic equation. Okay? The method that I've just shown you is called the reduction of order because you reduce a second order problem down to a first order problem. Now it's useful for discovering the form of the solution, but, and this is important, we're going to use more direct methods. Okay? Now a beautiful question here is use the reduction of order method to solve the general problem down the bottom where P and Q are just constants. Okay, they could be complex. Let's just, if you want to just treat them as real for the basic case. You'll see exactly where the solution comes from. Now, our analysis is going to concentrate on a special polynomial equation. Okay, it's a quadratic equation, and we refer to it as the characteristic or auxiliary equation associated with the ODE1. Okay, so essentially, here it is here, r's the variable, so you just take the coefficient of y double prime and multiply it by r squared. You take the coefficient of y prime and you multiply by r, and you take the coefficient of y and just write that coefficient down and set it equal to 0. Okay, so for example, this ODE here, let's look at the coefficients, 1, minus 5 and 6. Well, this would be the characteristic or the auxiliary equation associated with that. As far as from a practical point of view, what we would do is, given a ordinary differential equation, a homogeneous one with constant coefficients, you just write down the characteristic equation and then solve it for the unknown r here. So let me show you how we do that. There are different cases to talk about, remember. A quadratic equation can have a number of types of roots. It can have real and unequal roots. It can have real and repeated or real and equal roots. Or you can have complex roots. And each case demands a slightly different style of solution. Okay? So here's an example. Let's solve this first before we actually no. Let's look at this first and then solve that. This theorem says, okay, suppose I've got my characteristic equation and I solve it and I get two real and unequal solutions for r, r1 and r2. This theorem says that the general solution to the original ODE is just a linear combination of these exponentials with r1 and r2 in the exponent. Now that actually agrees with what we had on the previous question, okay? minus 2 and minus 3. The characteristic equation for that example would have given you real and unequal roots, minus 2 and positive 3. Okay, now this theorem, it might look pretty simple to you, and some of you may have seen it before, but it contains a lot of information. Okay, it's a really, really powerful theorem. So let's see how we can apply it and solve this particular problem. So if I was doing an exam or something, this is actually how I would solve it in an examination. Okay, so the characteristic equation of my ODE is the following. Okay, so it's going to be r squared minus 5r plus 6 equals 0. So my analysis now is moved from an ODE down to a quadratic equation. So we can solve this quadratic equation a whole bunch of different ways. You can factorize. You can use the quadratic formula if you want to. You might be able to complete the square. You can complete the square on some of these problems. It's up to you, whatever you feel comfortable with. Okay, so I'm actually going to factorize. Okay, two numbers that multiply to give positive 6 and add to give minus 5. Something like minus 3 and minus 2. Okay, so from over here, I know that the roots of my characteristic equation must be positive 3 and positive 2. Okay, now notice the form of the roots. They're both real numbers, 3 and 2 are real numbers, and they're unequal. They're not equal to each other. So we can apply this theorem up here, and this would be the general form of my solution, where C1 and C2 are arbitrary constants. Okay? So since our roots are real and unequal, the general form of y is the following. It's going to be, instead of having C1 and C2, I'm just going to write big A and big B. They're just arbitrary constants. Okay, so R1, let's choose R1 to be 3 and R2 to be 2. Okay. Now, does it matter which way you put the R1 and R2 in? Could I have A e to the 2x plus B e to the 3x? Of course you could. Okay, it doesn't matter which way you put the roots in, okay? Because A and B are arbitrary constants. Doesn't matter. Okay? So who's pretty comfortable with that? Who's got some good recollection of that from last year? All right, a few people. Who's never seen anything like that before? Anything like that before? Don't worry. Okay, you're learning now. We're all learning together. Now this is the case when the roots of the characteristic are real and unequal. If we had, say, repeated roots, this would not suffice. Okay. Now, like I said before, this theorem here, it contains a lot of information. It's very powerful. It looks pretty simple, but it's actually really powerful. Okay? What the theorem says that if you have real and unequal roots of the characteristic equation, the theorem says that all solutions to the associated second order ODE may be constructed from just a linear combination of exponentials. Okay? Now that's quite amazing. You can catch every solution every possible solution just by writing out a linear combo of special exponential functions. That's very powerful. Now, if you remember some linear algebra from first year, suppose V is just the set of functions that are solutions to the problem under consideration. That's a vector space. And this set here forms a basis of linearly independent functions that spans the solution space. So what does that mean? Well, it's just basically saying that you can construct any solution to the problem using a linear combo of exponentials. Okay, now, what do I mean when I say linearly independent? We've got functions here, right? So essentially, this holds. The only constants that make this true are the zero constants. Okay, so as an independent exercise, have a look at and see if you can solve that problem. We'll talk about it a little bit more at the end. But yeah, this is a very nice connection with linear algebra. Okay, what happens if we solve our characteristic equation and we get repeated roots, real and repeated roots? Well, the following theorem covers that case. In that case, we've only got one root, say r. It's almost a linear combination of exponentials, but note you've got this extra factor of x in one of the terms. Okay? Now, where does that form come from? Well, you can, if you want to, split up the middle term into minus 2y prime, minus 2y prime, and do exactly what, well, virtually exactly what I did in the original example by reducing the order. Okay? If you do that, you'll see exactly where that solution comes from. But let's say I had this in an exam and I wanted to solve it. You'll just write down the characteristic equation, solve that for the roots, and analyze the roots. Okay? So the characteristic equation of star is the following. So it's going to be r squared minus 4r plus 4 equals 0. Now I can factorize that. So something like this. So I get a repeated root. Okay, well that satisfies the conditions of that theorem, so we know that I can write the general solution as the following. Hence, the form of y is the following. So I'm just going to use big A and big B. So what will we get? We'll get something like a e to the 2x plus b x e to the 2x. Okay? Now, if you wanted to verify where this solution comes from, can use reduction of order. So what you would do is you would write it like, for this one, you would write it like this. Okay, so that is just the derivative of that. Okay, I'm not going to do that. That's something for you to look at. Okay? Now, again, there's a really nice connection with linear algebra. The previous theorem says that this set of functions forms a basis for the solution space, right? And it spans they're linearly a set of linearly independent functions that span the solution space. So essentially it means that if the roots are real and repeated, every solution to this problem can be written in this form. Every solution. Okay? Now the third case, the third case is when we solve the characteristic equation and the quadratic equation leads to complex valued roots. Okay? Now this is a little bit more, slightly more work, but you can see here I've got, if R1 is like A plus I beta and R2 is A minus I beta, remembering that for a quadratic equation the complex valued roots will appear in conjugate pairs, then you can take the alphas and betas and form a general solution through the following setup. So let's solve this particular problem. And again, if you want to know where this comes from, well, there's a couple of ways of formulating it. Again, you can use the reduction of order method, but it's a little bit trickier. But let's actually have a look at a particular problem and see how I would solve it. So the characteristic equation of star, well, that's going to be r squared minus 2r plus 5 equals 0. So I look at that and I go, well, I can't quite factorize that very simply. Now you might want to use the quadratic formula here if you want to, but I actually like completing the square. So what I do is I look at the coefficient of the r, it's minus 2. I take half that coefficient, square it, add it and take it away. Half the coefficient, square it, add it and take it away. So you're not changing anything. Okay, so half of that coefficient is minus 1. So I want to add minus 1 all squared and take away minus 1 all squared. Now I can actually simplify that even quicker. So complete the square to form the following. Well, what I can do is the following. I can split up that positive 5 into basically 1 plus 4, and 1 is negative 1 all squared. And then these first three terms, of course, are going to factorize. Okay, so I'll get something like r minus 1 all squared equals negative 4. All right, well, if you think back to complex numbers, what's that? So I've just taken this 4 to the other side. Okay, so if you think back to complex numbers, remember I squared equals negative 1. I can write minus 4 as something like 4 times I squared. Okay, so taking square roots and rearranging, I'll get something like this. Positive and negative square roots. All right, so in this case, my alpha would be positive 1 and my beta would be positive 2. So the roots are complex, hence the general form of the solution is the following. Again, instead of C1 and C2, I'm just going to use big A and big B. So I want to write that in terms of my alpha and beta. It's going to be E to the x times a cosine 2x plus b sine 2x. So here a and b are constants. Okay? So that's a standard method of solution there. Any questions so far? Okay, well, the slightly more difficult situation of complex roots actually, the original ODE admits complex valued solutions. Now, for example, these two complex valued functions will solve the original second order ODE. Now, what we can do though is write the solutions in the following form, and we're really only interested in real valued solutions, okay, for a bunch of reasons. So how do we actually come up with a real valued solution here? Well, what we do is we use these functions here, the u of x and the v of x. Okay, so think of this as your u of x and this is your v of x. Okay? And then just take any linear or all linear combinations of those real valued functions there. You can see if I factorize out the e to the alpha x, I've actually got all linear combinations here. Okay? So again, there's a beautiful connection with linear algebra, essentially saying that all real valued solutions can be constructed from a linear combination of these two special functions. In other words, these set of functions form a basis with linear independent entries that span the solution space. Okay? So this is important for making sure that, I mean, you know, let's say you come up with this representation. How do you know that I'm catching all solutions with that particular representation? Well, you don't, unless you have some connection with the linear algebra. Okay? All right, well, the linearly independent solutions are very important in this analysis. And it seems to make sense to try to come up with an easy test to test whether two functions are linearly independent. Okay? So to solve these problems, all I have to do is choose two functions that are linearly independent and satisfy the DE, and then form a linear combo of those. That's all I have to do. Okay? So how do I know that two functions are linearly independent? Well, you start with this equation here, and if you differentiate it, you'll get another equation. Okay? And what you want to do is show that the only constants, C1 and C2, that satisfy those boxed equations are C1 equals 0 and C2 equals 0. If you write it as a matrix, then we know that if the matrix here is non-zero for all x, then this system only has the zero solution, and so linearly independence follows. Now the determinant of this coefficient matrix has a special name called the Wronskian. Okay, named after the mathematician Wronski. this is an important determinant. Now we can even go a little bit further and prove, I'm not going to prove it, but it can be proved, that if this is non-zero at one point, or at least one point, then it's got to be a non-zero everywhere. Okay, so all you really need to do is test and see if the Wronskians, if you can find a point where it's non-zero, that implies that it's got to be non-zero everywhere. So here's another example. These two solutions from the case 3, where you have the complex valued roots, show that those two functions are linearly independent just by putting them in here, or just calculating these and looking and showing that the Wronskian's always non-zero in this case. Okay. All right, so if we have two solutions to our ODE, then every linear combination of these is also a solution. Okay, and I've sort of proved that here. Now, this kind of idea is known as the principle of superposition. It is superposition. But it's something that we're going to rely on heavily, especially when we get to the PDE's part of this course at the end. Okay, very important. If you have 2 or 3 or 4 or whatever, an infinite number of solutions, the law of superposition says you add them all up and they will form a general solution. So we'll look at this again. Now, some of you may be thinking, well, how do I calculate these general constants, the A's and the B's, or the C1s and the C2s? Well, you can uniquely calculate them by using the initial conditions. Okay, so let's say you're solving a problem and you know the solution at one point and its derivative. You can calculate C1 and C2. And in particular, if we use the following compact notation, so think of this L as some sort of operator. It's like an operator that operates on functions. This L basically takes y, it multiplies a function y by c, it differentiates the function and multiplies it by b, and it differentiates the function again and multiplies by a and adds everything together. This is a special operator known as a linear operator, in the sense that you can expand the fourth line. Now, just to reiterate, if y1 and y2 are solutions to our ODE, then this means that by the superposition rule, any linear combination of solutions is also a solution. Now, in the next lecture, we're going to use this L notation a lot because it saves a lot of space. You don't have to write down all the derivatives. Okay, so we'll have a look at that on Friday.